Hello, this video is just an introduction to Calculus 3. We will see what are the things we'll be covering under Calculus 3, which is a multivariable functions. So welcome to Calculus 3 course. In this Calculus 3, we have number of topics. The first one is vector geometry. The second one is vector functions. Third is a multivariable functions. The fourth is a multiple integral, and the fifth is vector analysis. So altogether we'll be having 5 chapters under this course. The first one, vectors and geometry of space. So in this first chapter, vectors and the geometry of space, we have the vectors in the plane. The vectors in the plane is all about using vectors. Vector is a quantity which has magnitude and direction. A very good example of vectors is force. The vectors in space, instead of taking the vectors in the two-dimensional system, we can consider the three-dimension and then talk about vectors. The dot and cross products. These are the different operations of vectors. The dot product is a scalar product and cross product will be your vector product. So a symbolic representation will be used like a dot or a cross to multiply two vectors. And then we have the equations of lines and planes in space. We have two different types of coordinates, cylindrical coordinates and spherical coordinates, apart from the Cartesian coordinates. The vector valued function has got vector valued functions and its calculus, the tangent and normal vectors, the arc length, and curvature. The functions of multivariable or several variables has the same introduction and limits and continuity, the definitions for limit, continuity, and problems what we have done in calculus 1. So instead of just two variables x and y, you'll have multivariables, maybe x, y, z, w, etc. And we will talk about the limits and continuity and the derivative, differentiability of it. But when we find the derivative, we cannot find that we can find the straight derivative in terms of its partial derivatives. That is, the partial derivative will be the derivative of one variable by keeping other variables a constant. And then we'll talk about the differentials. We'll have a chain rule. We'll have a gradient and directional derivative. We'll have the extrema of the function, the maxima and minima of the function. Maybe we'll also talk about a saddle point for this. In two dimension, suppose if the function is of the form f of x equal to x squared, we can find what is the limit of this function f of x. We can find the derivative of the function, straight derivative. We can find the line integral or integral f of x dx, and also we can describe the graph of the function in the two dimension, and then we can find various aspects of this. Maybe we can find the area under the curve, the length, arc length, etc., etc. But on the other hand, under multivariable, say if it is of two variables, it need not be of two variables. It can be three variables, say z equal to x squared plus y squared, or you have w in terms of x, y, z. In such cases, instead of taking the limit as x tending to 0, we can take limit as xy tending to some constant, some x tending to c, y tending to d, or something like that. And instead of finding the straight derivative, we may find the partial derivative, dou f by dou x and dou f by dou y. Dou f by dou x is the partial derivative of f with respect to x by keeping other variables or y and w and whatever we have, the rest to be a constant. The same way, if I find dou f by dou y, I am differentiating with respect to y by treating all other variables a constant. We can also find the derivative of the integral of this function f of xy, say with respect to dx or dy, or we can even find double integral dx dy, or we can even find triple integral of a function of xyz dx dy and dz. So instead of that a function in 2 dimension, we can find a multivariate curve representing the multivariate function, and then we can see the different aspects of that particular curve. So we have the multiple integrals, double integral, triple integral, and all that, and we can convert these from one system, a coordinate system, to a cylindrical system or a spherical system, and we get the area and the plane, double integrals and volumes, the change of variable using polar coordinates, surface area, the triple integral and its applications, and we'll also find the change of variables using Jacobians. The last chapter is vector analysis. It has vector field, line integrals, conservative vector fields, Green's theorem, Gauss divergence theorem, and Stokes theorem. These theorems, Green's theorem, Gauss divergence theorem, and Stokes theorems, will connect a line integral to a double integral, or a double integral to a triple integral, or a single integral to a triple integral. So those are the different methods of evaluating integrals. If we are finding it difficult to evaluate a double integral, maybe we can make use of one of these equations. You can use a triple integral or line integral. So these are the things we are going to cover in this Calculus 3. So in this video, we just saw an overview of how the course will progress in Calculus 3. I suggest that you should have a color graphing calculator so that we can see the different shapes of the curve, especially when we are doing a double and multivariable functions. Thank you for watching this. Thank you for listening.